This is the problem that we have. Okay. Hold on, focus. Okay, so first we're looking at 0 radians, and it says secant, so are we looking at the x-coordinate or the y-coordinate? X-coordinate. So secant corresponds to cosine. It's the same thing as cosine, right? But we're just the flipped version. So if we look at 0 radians and we look at the x-coordinate, and we take that value and we think of it as a fraction and we flip the fraction, what do we get? 1. Okay, so for the first part we have 2 multiplied by 1. Okay, next we have 4, and then this notation right here, cotangent squared of pi halves, this is like a shorthand notation that helps you to avoid having to write parentheses all the time. So what this notation actually means is it means that you're doing cotangent of pi halves and you are squaring the result. That's what it means. It's just a shorthand notation. So if we look at pi halves, what is cotangent? How do we find cotangent? X divided by y. Okay, so if we look at pi halves, what would x divided by y be at pi halves? It'd be 0, right? Because it's 0 divided by 1, so that would be 0 squared. Okay, plus. And then if we look at 2 pi, what is cos of 2 pi? Cos of 2 pi? What is it? We're looking at 2 pi, it's cos, so we're just looking at the x-coordinate. It's just 1. Okay. So 2 times 1 is 2. Okay. 0 squared is 0. 4 times 0 is 0. And so what is the answer for this problem? 3. Okay, let's try another one of those. I need to write the problem down. Okay, let's try 38. So sine squared of 2 pi thirds plus cos squared 2 pi thirds. Okay, so if we picture, well, you're not picturing, you have it in front of you, 2 pi thirds. What is the sine of 2 pi thirds? Look at your unit circle. Square root 3 over 2. So what this means is this is sine of 2 pi thirds, and then the answer is being squared. So we're going to write root 3 over 2 squared. Okay? And then over here, this is cos 2 pi thirds. So if we look at the unit circle, what is cos of 2 pi thirds? Negative half squared. Okay, so when we square fractions, we think about the fraction multiplied by itself. So we are squaring the top, we are squaring the bottom. What is root 3 times root 3? 3, root 9, which is 3. 2 times 2 is 4. Okay, 3/4 plus negative 1 times negative 1. 2 times 2. So 3/4 plus 1/4. 4/4, which is 1. Okay, that actually brings us to something cool that I think I might have gotten rid of the notes here even. But if you look back, remember the notes we did on the very first day of the, ooh, actually I still have. We're actually going to add to these notes if you can get them out. We'll see if anybody recycled these. I'm going to show you something really interesting. So these notes, do you still have these notes?
Oh, yes.
Somewhere, maybe they're still around.
I do, I've seen them yesterday.
Oh, see, so that's good. That's good.
So they're here, somewhere.
Yeah, didn't lose them yet. I spilled water on my desk before school started, and I didn't dry it up. I just kind of wiped it onto the floor, so it's wet over here. And then I'm just letting it dry.
Yeah, I was about to tell you.
yeah, and yeah, I just have been kind of just pushing it. He's fine. So when you get the notes out, we're gonna flip to the back. We're gonna look at this part. Because there's actually something kind of cool with this. If I lay this down, it's gonna get all wet. I'm gonna keep propping this up. Okay, so I'm gonna let it focus. There we go, focused, focused. Okay, so if we look at this little triangle right here, if I was to do the Pythagorean theorem on this triangle, do you guys remember what the Pythagorean theorem is? Yeah, a squared plus b squared equals c squared. So if we use these sides, how would I write the Pythagorean theorem? Okay, so I would write the Pythagorean theorem would be x squared plus y squared equals the hypotenuse squared, which for the unit circle we're going to say equals 1 squared or equals r squared, right? Okay, so so I just have x squared plus y squared equals 1. Does that make sense? Okay. Now, for the unit circle, what is x? For the unit circle, what is the x coordinate? Cos. So cos squared plus what is y? Sine. Sine squared is 1. Okay? Now, math people don't write it this way. They don't put it in parentheses because math people are like, why would I write parentheses when I can just not do that? So math people, when they write this, they never write it like that. They always say cos squared. We don't read it as cos squared theta. We just say cos squared. Cos squared plus sine squared equals 1. That's what we say. Cos squared plus sine squared equals 1. This is called a Pythagorean identity with trig. It's called a Pythagorean identity, and we just did a problem where we could see that it was true. My sticky note is completely wet right now. But if you look at this, we did sine squared of an angle plus cos squared of the same angle, and when we plugged the numbers in, we saw that it equaled 1. And as long as you do that with the same angle, it will be true every single time. And it's because of how the triangles work. It's because of the Pythagorean theorem. That's why we call it the Pythagorean identity. It's called theta. It's a Greek letter, and it's the variable that we typically use for an angle. Yep, theta, T-H-E-T-A, theta. It's just a variable that we use for an angle. Yeah. All right, so this is called the Pythagorean identity. And if you look at your blue sheets, I don't have one handy over here, but if you look at your blue sheets, oh, thank you, I will not get it wet. The Pythagorean identity, we have it right here. It will become your favorite. It's very important. So sine squared plus cos squared equals 1, or cos squared plus sine squared equals 1. It's a really important thing in trig to memorize that, to know that that's always true. So Pythagorean identity, that's where it came from, and that's what it was actually in that problem, which is kind of interesting. Okay, let's go back to that worksheet. Are there any other problems on the worksheet that you guys would like to look at? Number 32? Okay. Okay, cosecant theta equals negative 2 root 3 over 3. So what we're doing, focus. What we're doing is we are looking at the unit circle. This is cosecant, so this is the flipped version of sine. So we are looking at the y-coordinates, where if you flip the y-coordinate, it would simplify to become this. If you flip the y-coordinate, it would simplify to become this. So what do you think the fraction is that would flip and then simplify to look like this? Would it be 1? No. Would it be 1/2? No. Would it be root 2 over 2? No. Would it be root 3 over 2? Yes. So you don't necessarily have to see this on the unit circle. You just have to use like trial and error or your powers of deduction to think about, oh, what would flip to make this happen? It would be root 3 over 2. I don't have to do the work for it. I just have to recognize what would happen. So, and we're looking for the negative version. So we're looking for y-coordinates because we're looking for cosecant. So we're looking for y-coordinates that have negative root 3 over 2 because they would flip, and then you'd have to do the work to fix it to become this. So where are there y-coordinates on the unit circle that are negative root 3 over 2? Not 2 pi over 3. Y-coordinates? 4 pi over 3 and 5 pi over 3. So those are your two spots. Does that make sense? Okay. All right. You don't have to turn those in today. Right now, if you need some more time to be able to do those other two sections, that's totally fine. Okay. Go ahead and clear off your desks completely. But I want to show you guys where the sine graph comes from. So we're going to grab our unit circles. And is sine the x-coordinate or the y-coordinate? The y-coordinate. Okay, so when people graph sine, they go for the easy points, which means they don't typically use these coordinates, these y-coordinates for sine right here. I mean, 1/2 actually isn't bad, but root 2 over 2 is not going to be fun to graph. Root 3 over 2 is not fun to graph. So what they typically do is they go for the quadrant points. So they go for a radian of 0, and they say that if sine has an input, if the angle is the input, sine of 0 radians, then the y-coordinate there is an output of 0. And so that would be this point right here, 0, 0. And then they say the next point that they're going to do, they're going to skip the 3 right here. They're going to skip that sine of pi 6 is 1/2. They're going to skip that sine of pi 4ths is root 2 over 2. They're going to skip that sine of pi 3rds is root 3 over 2 because those are all not as fun to graph. And they're going to go straight to this one, that sine of pi halves is 1, because that's the next one right here, that sine of pi halves is 1. That's the next one that's easiest to graph. So the input is pi halves, the output is 1. But we could, if we wanted to graph these just to see if we're like kind of accurate, here's where pi 4ths would be. And if I wanted to graph that, I could see like square root 2 divided by 2 is 0.7-ish. And 0.7 is maybe here. So I could see that like pi 4ths and 0.7, you know, root 2 over 2, like that fits the graph. It makes sense. That point is on there. But people typically don't graph that point just because it's not easy. The next one that they would graph for sine is they would go over here. If we plug in pi, then our y-coordinate is 0. So right here, if you plug in pi, your y-coordinate is 0. And then next, if you get down here, 3 pi halves, your y-coordinate is -1. 3 pi halves, your y-coordinate is -1. And then we get back to where we start our coterminal angles. So our first coterminal angle is 2 pi, and our y-coordinate is 0. 2 pi with a y-coordinate of 0. Oops, I didn't label this one. 3 pi halves, -1. and then 2 pi 0 is right here. And remember that 2 pi and 0 are coterminal. So we did like the whole like cycle of the graph, and then once we get here, that shape would actually start over again. And it would do the same shape, it would just continue on in radians that are a little bit bigger. So 2 pi would be next, and then it would do 5 pi halves, and then 3 pi, and then 7 pi halves, and then 4 pi, and it would keep going, and it would keep making this wave shape, just over and over and over, the same wave shape. Does that make sense? So that's kind of how sine works. So what we do when we graph sine is we say, okay, this is called one period of the graph, and we just say it has like one cycle there, and that's what we're interested in, is just to show like, okay, this is a shape of the graph. We went around the unit circle. We know what the shape of the graph looks like, and we know that it just repeats itself. So when we graph it, we always graph a couple of these to show like, yep, that graph repeats itself. We got it, it makes sense. And we can draw a couple of those without messing it up. We can make it look like a smooth wave that repeats itself multiple times, and we understand that that's how it's supposed to be. So when you're dealing with these different trig functions, we typically focus on sine and cosine. Sometimes we look at trig, and that's what we're going to do in Math 4. These are some words that are important for trig functions. So the first word is amplitude, and for us, that's going to kind of replace the idea of vertical stretch, although they're not quite the same thing. So this right here, from here to here, from here to here, this is the amplitude. So an amplitude of 1, a distance of 1 from the middle of the graph to the highest point, or the middle of the graph to the lowest point, an amplitude of 1 is normal. And then any amplitude that's different, you could say it's being compressed or it's being stretched. But we don't typically call it stretch or compression. We just say that the amplitude has changed. So they call it an amplitude. The other difference is we never say, well, I guess this is kind of the same actually, and versus calling it like a stretch or compression. We never say it's like bigger or smaller. We just say the amplitude is always a positive number that could be a bigger or smaller positive number. So there's no such thing as a negative amplitude, although you might notice that the number in the front might be negative. All that's going to happen if you have a negative number in the front is that this loop up here might go down first. That's what a negative in the front would do. It would reflect it over the x-axis, just like we're used to. So a negative graph would go down first and would then go up. It would make the wave start in reverse from what it normally would, okay? So the amplitude is the distance from the middle of the wave to the lowest or the highest point. That's what the amplitude is. For us, it's going to look like what we're used to looking for, which is where we look for the vertical stretch or compression. So A, the absolute value of A, not worried about if it's positive or if it's negative, the absolute value of A is our amplitude. If there's no number there, then it's just 1. 1 is normal. Okay, the period of the graph is the length it takes to do one full cycle like this, to do one full wave. So it's normal for the graph to do one full wave from 0 to 2 pi. That's a typical period of the graph. But they can put numbers in the problem that will change that. Okay, so the period is the length of one cycle. It's easiest to pick a point and then measure how long it takes to get back to that corresponding point for the pattern to start over again. So for us, we said 0 to 2 pi because after 2 pi we can see that it starts going up again. Right here you can see it starts to go up again and form the same pattern. That's where we completed the unit circle and we got to the coterminal angles. So the period can be affected or it can be impacted by the B value in front right here. Okay, so the period, the formula for the period of the graph is you're going to do 2 pi divided by the b value. And for trig functions, we don't talk about horizontal stretch or compression. We don't use those words. All right, we just talk about the period of the graph. And the period of the graph really is how wide. If the graph is like stretched out, the period is really wide, or if the graph is squished, the period's really short. We don't talk about horizontal stretch or compression, but that's basically what it is that the period of the graph is changing. All right. There's another thing called frequency. It's the number of the waves that you have, the number of cycles that you have in 2 pi. So a normal frequency is 1. A normal graph would just have a plain old x in it, sine x. But if you start to have other numbers in there, if you have like sine 2x or sine 3x or sine 5x, then you start to make it so that there's more and more waves from 0 to 2 pi. So if you had sine 5x, then your period of the graph would be 2 pi divided by 5. It would be 2/5 pi for 1 cycle of the graph. And then you would have 1 cycle for 2/5, and then another cycle for 4/5, and another cycle for 6/5, and another cycle. And if you count those all up, you'd say, oh, I get 5 of those cycles from 0 to 2 pi. So this b value we call the frequency. It tells you exactly how many of these full pictures you're going to get from 0 to 2 pi. It's normal to have 1. If you have a different number here, then you'll just have more. So if we have a 2 there, then you're going to have 2 of those waves from 0 to 2 pi. If you have a 3 there, you're going to have 3 of those waves from 0 to 2 pi. All right, so the frequency. And then the midline is right here. Hold on, I ran out of lead. Let me grab this. The midline is right in here, and it's the middle of the graph. It would be like the imaginary line that cuts the graph in half horizontally. And if you want to use your marker, that's not a bad idea. When we write the midline, when we write down what it is when we find it, we're going to write the equation of a horizontal line. So for this particular graph, for the parent function, we would say that the midline is y equals 0. All right, and then if you want to label the period and frequency in here, we could say that this is the period of the graph. And if you want to write something like a frequency of 1 is the default, you could write that. Okay, so B is the frequency. This is good to write. That's kind of like a formula. And then just like we're used to, the H value, a positive H moves to the left. A negative H moves to the right. For the K, a positive K shifts up, a negative K shifts down. So some of those other transformations are what you are used to from Math 3. But these other words are new vocabulary for us. Okay, so when we graph these sine functions, we are specifically going to look for these 5 points because those are the easiest. And they're actually not terrible to draw. They work pretty easily. Okay, so let's go ahead and try this first graph. So I'm going to draw my x-axis, and this is what I would use the marker for. I'm going to draw my x-axis right down the middle. And the same thing with my y-axis. I'm going to make that approximately in the middle. And then if I look in the very front of the equation, there's no a value. There's no number here in the front, which means that the amplitude is 1. the period of the graph is 2 pi divided by b. So in this case, it's going to be 2 pi divided by 3. And so the period of the graph is 2 pi thirds. The frequency of the graph is b. The b value is the number that's the coefficient for x, and so 3 is going to be the frequency. So if I graph the whole curve from 0 to 2 pi, I'm going to see that it has this wave up and then down. It's going to have this wave 3 times from 0 to 2 pi. And then the midline is always whatever's at the end. It's the k value. So if you are centered at 0, then the midline is going to be 0. If you shift the whole graph up 1, then the midline is going to be 1. If you shift the whole graph down 5, then the midline is going to be -5. Does that make sense? The middle of the graph is wherever you vertically shift it. So the midline for this graph is going to be y equals 0 because this graph is not being shifted up or down at all. It's going to be right in the middle. Okay? All right. So what I always do is I look at the period of the graph and I use that period to label my x-axis. And when we draw this, we are always going to start with the period of the graph and we're going to put a dot at the beginning and put a dot at the end. And then we're going to put a dot in the middle. So we need to have a number of boxes that we can divide in half. Okay? And then from there, we're going to be dividing each of these waves in half to put this point, in half to put this point. So we need a number of boxes that can be divided in half once and then divided in half again. Does that make sense? So whenever I choose the number of boxes that I'm going to use for the period of my graph, I'm going to use 4 boxes, 8 boxes, or 12 boxes. I'm always going to do that because I need something that can be divided into 4 groups. Divided in half and then divided in half again is divided by 4. Does that make sense? So I'm going to do 4 boxes, 8 boxes, or 12 boxes. Okay? So for this one, I'm going to go ahead and do 4 boxes. So I'm going to count 1, 2, 3, 4 boxes and put 2 pi thirds. 1, 2, 3, 4 boxes, 4 pi thirds. 1, 2, 3, 4 boxes. This would be 6 pi thirds. What is 6 pi thirds? 6 thirds is 2. Okay, so this is 2 pi. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3. Need to go over 1. I wrote the wrong number anyway. Okay, 2 pi. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. For my amplitude of 1, that means that when I go up and down, I'm going to go up and down by 1. So I can count 1, 2, 3, 4. I can count like that. Or I can count 1, 2. Or I can count up here and just go 1 and make my graph look really tall. It does not matter. Okay? So what I'm going to do for this first example is I'm just going to do 1, 2. Now, when you guys do these graphs, you have to label your x and your y axes. There's no way around it because these graphs are all going to depend on the labeling. All right? So there's no way to avoid doing your labels. All right. So let's look back at the sine graph. The way that the sine graph works is it starts at 0 and it ends at the end of the period. So starts at 0, ends at the end of the period, and it's on the midline. So I'm going to start at 0, I'm going to end at the end of the period, and I'm on the midline. Okay? And then halfway in between those, it cuts into 0 again. So halfway in between these points, I'm going to cut into 0 again. Everyone good so far? Okay. Between the first 2 points, it does a wave. So between these first 2 points, it does a wave, and the wave is the amplitude of 1, unless it's a problem that has a different amplitude. So between these first 2 points, it's going to go up the amount of the amplitude. So between these first 2 points, we're going to go up 1 because our amplitude is 1 for this problem. Between the second 2 points, it goes down the amount of the amplitude. So that's our whole first wave, and then we make sure that we connect these with kind of U shapes. They should not be V shape, they should be U shape. And then we do it again. Okay, so we've got the beginning, we've got the end. We cut it in half for the middle. Between the first 2 points, we go up the amount of the amplitude. Between the second 2 points, we go down the amount of the amplitude. And then we've got our U shape and our U shape. Okay. Starting, we've got a point at the end. We've got a point in the middle. Between the first 2 points, we go up the amount of the amplitude. Between the second 2 points, we go down the amount of the amplitude. We've got our U shape. We've got our U shape. I'm going to show that this continues. And you can even keep going over here. Between the first 2, it goes up the amount of the amplitude. It goes down the amount of the amplitude. And you'll know that you did it right because you can trace it with your finger, and your finger just goes up and down. Your finger doesn't stutter, your finger just goes up and down as you trace it. All right, how did we do? We got it? Okay. Everybody show people at your table what it looks like. Do we have smooth curves? We don't have any jagged curves. This is not a chevron pattern. We don't have Charlie Brown's hat or t-shirt. It's his t-shirt. No Charlie Brown t-shirts? We got it?
What, is... I don't understand why there's 4 of those things.
Because you would keep going around the unit circle. So
Technically, it'd forever keep going.
it'd keep going forever.
We just stopped right there just because we felt like it.
Yeah, I put arrows because this is really... Yeah. So I went to 2 pi so I could show you that here's that frequency of 3. It did 1, 2, 3. And that's because there was a 3 in front of the x. So from 0 to 2 pi, it did 3 of those little waves. Mm-hmm.
And then the other ones behind are going to do the same thing.
Mm-hmm. There would be 3. Mm-hmm.
And so it goes to negative 2 pi.
Yeah. But you don't have to do that many. The typically what the general requirement is that you draw at least 2 of them to show that you understand it's a pattern that continues past just 1. Yeah. Okay, let's turn to the next one. All right, so this one, I'm going to rewrite this one slightly differently because this one has a coefficient with x, but it's kind of written as a denominator with the x. So this would be -2 sine, and then if we wrote this as a coefficient, that would be 1/2 times x. So now we've got to be careful about figuring out what the period of the graph is. So amplitude, there's a 2 in the front. We don't take the negative with it. We just look at the size of the number. So the size of the number is a 2. So this graph is going to start in the opposite direction. The wave is going to go down first, not up first. It's going to be opposite. The period of the graph is 2 pi. I'm going to write it up here. It's 2 pi divided by b. And our b value is 1/2. So it's going to be 2 pi divided by 1/2. So what do we do if we divide by a fraction? Yeah, we multiply it by the fraction, so we keep it, change it, flip it. So keep the 2 pi, change it to a multiplication problem, and flip the fraction. And so what is the period of the graph? Four pi, okay? So the frequency for how many waves we're going to get is 1/2. So from 0 to 2 pi, we're only going to get half of the wave. We're not even going to get the full thing. The midline, again, is going to be y equals 0. This graph is not shifting up. It's not shifting down. It's going to be right in the middle. So I'm going to go ahead and draw my x-axis right in the middle. And this time I'm going to use 8 boxes to make 4 pi. So I'll count 1, 2, 3, 4, and I'll put 2 pi right here. And then I'll count 1, 2, 3, 4, and put 4 pi right there. So it would be really obvious in this type of assignment if you were copying work from someone else, because all your graphs would look the same. If students were naturally doing this, all the graphs would look a little bit different because you wouldn't necessarily choose to make your intervals the same as somebody else. So some students really like to do their intervals in 4s. They're like, I'm going to do my intervals 4 every single time. Some students change it up every single time. They do like, oh, that's really spread out, so I don't want to do that, or I like my graphs to be spread out. I tend to, for mine, change mine up every time just so that so it helps the most number of students, so it doesn't feel like one student never gets to have theirs look like the answer key. Okay, so we're going to put a dot at the beginning. We're going to put a dot at the end. We're going to put a dot in the middle, okay? And then, I have to label my y-axis as well. So we can do 1, 2, 3, 4, that's one option. Or we could do 1, 2. What do you guys want to do? 1, 2, 3, 4, or 1, 2? 1, 2? Okay, so we're going to do 1, 2, and 1, 2. Okay. So I've got my dots started. Now normally between the first 2 points we would go up to 1, up to an amplitude of 1, but this has a negative in the front, so what are we going to do? We're going to go down. We're going to reflect. So we're going to reflect and go down to our amplitude of 2. And then between the second 2 points, we would normally go down to our amplitude of 1. But now we're going to go up instead because we're reflected, and we're going to go to an amplitude of 2. So there is one cycle of the graph, and you can see for our frequency that from 0 to 2 pi, we only got half of the picture in. We didn't even get the full picture, just half of it. Okay, and then I can go ahead and do it again. So beginning, 1, 2, 3, 4. 1, 2, 1, 2. There's 8 pi. So beginning, end, middle. Between the first 2, I'll go down. Between the second 2, I'll go up. And you could do another cycle over here. All right, how do we feel about these? Feeling okay? All right, this one, what is the amplitude? 3. Okay, how do we find the period of this graph? 2 pi divided by the b value, and then what's the b value? 2, the b value is 2. 2 pi divided by 2 is pi, okay? So the period of this graph is going to be pi. And then the frequency of the graph is just the b value. So what's the b value? 2. So from 0 to 2 pi, you're going to have 2 sets of the waves. All right? And then what is the midline? 1. Y equals 1. So our graph is actually going to be shifted this time. So I'll show you how that's going to work. It needs a y equals. Yeah. Okay. So I'm going to go ahead and put my marker right in the middle. Okay. Do you guys want to do 4 boxes? Do you want to do 8 boxes? We could really spread it out and do 12 boxes. What do you guys want to do? 4. Okay. We're going to do 1, 2, 3, 4 boxes, put a pi. 1, 2, 3, 4 boxes, put a 2 pi. 1, 2, 3, 4 boxes, put a 3 pi. Okay. We have to be able to move, like have our midline at 1, and then we have to be able to graph an amplitude of 3. So should I do 1, 2, 3, 4, or should I do 1, 2? I should do 1, 2, 3, 4. Because I have to have an amplitude of 3 and I need to have enough space for that. Okay, so whenever I have a midline, this is what I do. I take the midline and I draw a dotted line where the midline is. So in the past, I've used dotted lines as asymptotes. This is not going to be an asymptote. This is just the midline. This is just the middle of the graph. And this is not really part of the graph. This is just helping me locate what the middle is. Now, when I do my dots this time for the middle, I am not going to draw them on the marker. I'm going to draw them on the midline instead. Okay? So I'm going to say begins at 0, ends at pi, and then hits in the middle. So I'm still doing my 3 points like normal. So begins, ends, and then the middle. And then what do I do between the first 2 points? What do I do between the first 2 points? I go up to my amplitude, which in this case is an amount of 3. So I'm going to go, 3 is 3 boxes. So I'm going to go 1, 2, 3 boxes. There's my amplitude. What do I do between the second 2 points? It goes to 4 because that's an amplitude of 3. And then what do I do with my second 2? I go down my amplitude of 3, so 1, 2, 3. Okay, so there's my full wave. And then I'll do it again. So beginning, end, middle. Between the first 2, I'll go up the amount of the amplitude. Between the second 2, I'll go down the amount of the amplitude. Beginning, end, middle. Between the first 2, I'll go up the amount of the amplitude. Between the last 2, I'll go down the amount of the amplitude. Okay. How do we feel? We good? Okay. All right, let's try this one. What is the amplitude? 1. Okay. Let's find the period for this one. It's kind of a weird problem. So we're going to do 2 pi divided by the b value. What's the b value? Pi over 2. So how do I divide those? I'm going to multiply. So I'm going to do 2 pi times 2 over pi. Okay. What happens to the pi's? They cancel out. And what do I get? 4. Okay, so the period of the graph is 4. It doesn't even have pi's in it. The frequency is kind of abstract for this problem. We're not going to be able to see it very well. What's the frequency? Pi over 2. Okay. What's the midline? Y equals -1. Okay, so I'm going to draw my marker. Now, sometimes if the amplitude is big enough, like if I ever gave you an amplitude of 5, and then the midline was big enough, you might have to move your marker lines up or down. What I typically do is I put them right in the middle unless I have to move them. Like unless I absolutely have to move them. I'll leave them in the middle otherwise. Okay, so for a period of 4, do you want to do 4 boxes, 8 boxes, or 12 boxes? 8 boxes? Okay, so we're going to do 1, 2, 3, 4, and put 2. 1, 2, 3, 4, and put 4. 1, 2, 3, 4, and put 6. 1, 2, 3, 4, 2. 1, 2, 3, 4. 1, 2, 3, 4. Okay. For an amplitude of 1, and a midline of -1, do we want to go 1, 2, 3, 4 or 1, 2? 1, 2? We're going to go 1, 2, 1, 2. Okay. So now we have to do our midline of -1. So I'm going to put my dotted line in here at -1. Okay. All right, so what do we do? Should I draw on the marker or on the midline? On the midline. Okay, so at 0, and at 4, and at 2. So beginning at the end of where the period is, and then right in the middle. Okay? And then between the first 2 points, what are we going to do? Be careful, we're going to go down. Why are we going to go down this time? There's a negative in front of the graph. So we're going to go down, and we're not going to go down 1 box. How many boxes do we go down? 2 boxes, not because the amplitude is 2, but because of the way that we scaled it. We scaled it so that 2 boxes equals 1. Okay? So we're going to go down 2 boxes for an amplitude of 1. This has been reflected, so we go down first. We go down 2 boxes for an amplitude of 1. Okay? What do we do between the second 2 points? You guys are like, we like to say it silently. We go up, yeah. So many people told me that answer silently. Okay, we go up 2 boxes. So there's our curve, okay? And then we'll do the pattern again. So beginning, end, middle, down an amplitude of 1, up an amplitude of 1, okay. Let's see. I think that's a good stopping point for today, actually. So I'm going to hand out the assignment, and you guys are going to do, this is going to be some really tough homework. You guys are going to do the first 2 problems on the assignment. Sound reasonable? All right. That's what we're going to do.